What I'm going to do now is go through a number of, at first maybe seemingly unrelated little issues, but there are a lot of little things we need to know to put together our first program. So let me go over those in a fairly short lecture. This is still background material, but let's start with this. I mean, we're starting with the idea that we're going to be writing an application program. It's going to talk to a graphics library and then go through various stages to come out. Now, if this was the traditional OpenGL that you were running, desktop OpenGL that you might be running on a personal computer, then the organization might look like this, that the job of your OpenGL library was to get OpenGL functions down to the OpenGL drivers, and the drivers would handle the input and the output devices. If you looked at it from the left side of our application program, then you might see something that looked a little more like this. This is what we're not doing now, but any of you who took 412 or another graphics course probably saw something like this, where the OpenGL application program would produce a bunch of function calls to libraries, the core OpenGL library, another library that for teaching, many people use a library called GLUT to provide the input services and windowing services that you need. Then you'd have another library, GLUE, that would sort of, especially with Windows implementations, would sort of tie everything together. Then if you were running on a Linux system, you would probably be using X underneath, so there'd be another library here, GLX, which would sort of glue everything together between the OpenGL side and the X Windows side. And finally, things would go out to some drivers and out to things. So it was, in one sense, it was a kind of a complicated model because you needed all of this stuff. But on the other hand, from the point of view of the application program, you would be making calls to just these three libraries, primarily the GL library for your actual action graphics, your GLUT library for interactivity, and perhaps the GLUE library just once or twice to get things started. And then I'll look at the model in a second for WebGL, which is going to be very, very different. But what we're going to focus on is an incredibly simple program. This one happened to be produced using desktop GL, but it'll look essentially the same there. And we just want to put a square up on a solid background. Now here was sort of what it used to look like with fixed function OpenGL, and let me just say it, go through this because it's in contrast to what we're going to be doing. So you included a bunch of stuff that had all the parameters you needed for the various libraries, but here's your basic display process, that you would clear the screen, you would specify a quad, missing parenthesis here, you'd specify a quad and you just say vertex, 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 and say there's the end of my quad. And as we talked about, I think 2 lectures ago, as soon as each vertex was specified, it would flow down the pipeline. The quad, the begin and the end, would now say this is a quad, here's the end of its specification, and so we could do primitive assembly further down the pipeline, and that was basically it. The control of this would just say, let's put a window up on the screen. These are all through the GL library, so they just begin with a GL, these functions. These are in the GLUT library, so they begin with GLUT. We'd create a window. We'd say what we want to display in it is this function up here that we just went through, and then enter into an event loop, which I'll come back and talk about in a few minutes. So this would just, basically enter that loop and nothing else would happen, and that's about as simple a program as you could get. Now, of course, it would be relying on things like knowing that the background by default would be black, and the color that it would fill this rectangle with would be white, but we could use those default values to at least get a simple program. But the problem is this isn't going to work. for a couple of reasons. One of which is that because we're going to retain mode and we're using WebGL, which is based on a fully shader-based model, and we want to make use of the GPU and have a much more modern program, virtually all these functions back here have been deprecated. Vertex doesn't exist anymore in WebGL and in OpenGL 3.1 and up. Begin and end don't exist anymore because these are old immediate mode functions. We're not going to be using this library anymore, so almost everything here is gone. Well, what happened? Well, these functions were deprecated, and we're not going to no longer be able to say, well, I'm going to rely on a bunch of default values for the colors and for the, we didn't say anything about what the values actually mean for viewing and for the window. We're just not going to, they're not there anymore. We're going to have to specify everything there. However, the basic function of using an event loop to process is still the same. So let's do an overview of what it would look like now within the browser. So this is a WebGL implementation, and it looks something like this. You're running here in your browser. You see a URL of, say, you're going to my website, you're going to run one of my programs. So you go over to my website, you look at the URL for that, you click on it. What comes back is a web page, which is going to be an HTML file, which will be now run in the browser. Now, inside of the browser, it's going to read some other files that are out there. It'll tell it to read a JavaScript file and bring in some utilities and things like that. And all of that will eventually go through some sort of a JavaScript engine that will then send commands out to the CPU and the GPU and eventually put that information in the frame buffer and go through some sort of an event loop that will display this information as needed. Now, one thing to note here, and again we'll come back to this later, is that this is running within the browser environment. So what you're doing here is looking at a web page that's written in HTML, the hypertext markup language, in particular HTML5, which supports a canvas element. Now that canvas element provides a drawing surface, and that drawing surface can be used by a number of different programs or packages concurrently, if you like. It happens that in HTML5 it supports WebGL too. So we can think of our frame buffer as being part of this canvas, or perhaps maybe a little more correctly, that the frame buffer might be up here attached to the GPU, but it gets copied to a certain part of the canvas, while other things might get copied there too. For example, if we want to put text on top or something like that. But for now, this is kind of the model. Now, the action here is that we're going to be in some sort of an event loop. We'll be talking in about a week more about input and events and buffering. But the basic idea is that you go to a form of programming which is very different from the imperative form of programming most of you do, where events are controlling the flow of the program. So we'll put something in the frame buffer and then wait for something to happen. The things that could happen might be someone presses a key on the keyboard. It might be that something happens inside the program. There might be a timer. There might be some desire to get input from a mouse. And the way this is all done is to generate events and respond to those events. So every program will be characterized, at least maybe except the first trivial one, of having event loops in them and functions which are called callback functions, more in the Unix kind of community, but they're also called more in the web community are called event listeners and sometimes callbacks. So every program you're going to write will have a render callback, which will render the scene when asked to. So in a static application like just drawing that that cube once, we just execute the render function once. But in a more dynamic setting where things are happening, or we want to move that cube or rotate that cube, then the render function is going to be usually it'll call itself recursively, and each redrawing is going to be triggered by some sort of an event that could happen, whether it's a keyboard or a mouse event or something happening within the Windows system. And we'll be going through that very, very soon. Now, what we're going to turn to now for a minute, and as I said, there's a lot of little things in this lecture, is look at the functions. Now, OpenGL is not object-oriented, and even though we may be using object-oriented languages to work with OpenGL, C++, say with desktop OpenGL, or WebGL is using JavaScript. JavaScript is an object-oriented language. OpenGL, all versions are not object-oriented. There are a lot of reasons for that. Historically, it was one of efficiency. So there'll be multiple forms of functions available. And so here's a simple example. Uniform is a function we use to send data to a shader. And so it will look like this. GL will be the graphics object, or the graphics context. And it will have a member function called uniform, but it'll have various forms of uniform. So gl.uniform3f will say, I want to send 3 floating point numbers to the shader. Uniform2i will say, I want to send 2 integers to the GPU. GL uniform 3, that should be an F. No, 3, this should be an FV. Oh, actually, this would be more like in a desktop OpenGL. This would be 3 doubles that are being sent, but they're being sent through a pointer. So essentially, this would be saying, I'm sending you an array of 3 double precision numbers. Now, so there are varying forms of the uniform and function. We have 3, usually we can send 1, 2, 3, and 4 dimensional entities out there. We can send them as integers or floats. This is important for the GPU. Often what we'll find is that underlying that, the storage mode is the same. So these will refer to what the values look like in your program. And we'll see more of that. But there's, even though you're working with an object-oriented language, WebGL itself is not object-oriented. So the function format will look something like this. It will, GL here will be the OpenGL context. It will refer to the GL context, or the GL object, and all of the OpenGL functions will be in here. Uniform is the name of the function, 3 is the number of variables, and F says what type of variable we're sending. If there's also a V there, that will say it's a pointer to an array. Okay. Now, there's a lot of constants in OpenGL and WebGL. In desktop OpenGL, we put a whole bunch of them in a file generally called gl.h or glut.h that's included. Rather than use magic numbers, all of these constants are given strings that go in include files. In WebGL, they're placed inside of the GL object, so they will be referenced here. As seen in desktop OpenGL, suppose you want to enable some sort of a function. Here I want to enable depth testing so I can do hidden surface removal. So I'd say, well, the function I want to call is GL enable, and the parameter I want to send will have a name, GL underscore depth test, and that's defined inside this gl.h file. In WebGL, we have exactly the same functions because we're just implementing ES 2.0, but the format is different. So we have the GL object enable, has an enable function in it, and now also within that context are all the parameters. So it's GL dot to say it's inside of that object, and the parameter name is depth test. So it's pretty much exactly like it was in in desktop GL. Here's another example of clearing the screen, of clearing various buffers. Happens to be only clearing the color buffer. So the GL context, the function name is clear, and the parameter we want to send is the string gl.colorBuffer bit that says clear all the colors in the frame buffer. We'll also want to clear other things later, in particular the depth buffer when we're doing hidden surface removal. Okay, now next thing we want to look at for a second is WebGL and GLSL. Now, WebGL, because it requires shaders, the shaders are going to be written in the OpenGL shading language GLSL, and we have to have at least two of them. Previously, OpenGL was based very much on a state model where you set various parameters, and the parameters were persistent until changed. So you could set the present color, or you could set a matrix, and the matrix would be set. WebGL and the more modern versions of OpenGL have gone away from that, somewhat in the sense that if you want to have some state variables, just define them yourself. They're not predefined within the system. And as we've said, the action happens in the shaders, so you're going to have to write GLSL code. And one way to think of it, that basically all the application is doing is trying to get data to that GPU and sort of control the flow of the program, but the actual graphics is going on inside the GPU. So what does that language GLSL look like? We'll be talking about that starting next week in great detail. Well, it's very much like C, but it adds a few things that make it very nice. It has basic matrix and vector types added on. So the atomic types are not just ints and floats, but they also include 2, 3, and 4 dimensional matrices and vectors. So you could have vec2a, which would define a 2-element vector, and likewise for matrices. In addition, what's very, very nice is that the operators are overloaded. So all of the standard matrix and vector operations and combinations of operations between matrices and vectors and the other types all have overloaded operators. So if A and B are matrices of the same dimension, you can just have a matrix C and write C equals A plus B, and everything will be fine. So the code becomes very nice and very short, and doesn't, not only is it a lot more efficient, but you don't have all these loops in your program. You also have C++-like constructors. But other than that, it's basically like writing C code or Java code. Okay. There are two other versions. NVIDIA started one early called CG, but that's starting to get less important as GLSL becomes so linked with WebGL. Microsoft, of course, has its own shading language, HLSL, but because it developed them in conjunction with SGI and NVIDIA, it's very, very close. And also the shaders will pretty much go across the different OpenGLs. They don't there's different versions of the shaders, but there's a version directive that you can put inside the shader, and you shouldn't have to change shaders when you go between desktop GL and WebGL. Now, the code is sent to the shaders, well, as source code. What WebGL does is, well, it's not quite right. What WebGL you have to do is the shader comes in as ASCII code, or just basically it's just a text. It's compiled inside of the drivers, and that means so there are WebGL functions to read in your shaders, to compile the shaders, link the shaders, and put everything together in what's called a program object, which would then have in everything, all the information it needs to get the variables back and forth between shaders and the application. So we're going to have to talk about those functions. But in one sense, it's very simple, because you're going to write code that's readable and just send it on to your application, and it will hopefully compile and